Hey guys, this is Nivi Prasad and this is my Lab 5 Create Your Own Adventure lab. I use the Slinky video. So for the goal of this lab was to examine the motion of a stretched Slinky that has a tennis ball attached to the bottom of it while keeping in mind that the Slinky is dropped from static equilibrium. The result was that the bottom of the Slinky did stay stationary. The observed collapse time was about 0.23 seconds, which corresponds to the time required for the waves to propagate down the Slinky to communicate to the release of the top part of the Slinky. The following principles helped me start my code to analyze the video. So I used Newton's second law, which states that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force to update my velocity and to update my position. I also used gravitational weight formula is equal to the gravitational constant negative, 9.8 meters per second square times negative because it's going in a downwards direction times the mass of the object. Here is the tracker video. As you can see, as the top of the Slinky is going downwards, it is pretty linear, the line that it makes. And when it comes in contact to the ball, you can see the ball starts off going in a straightish line, but when the force of the Slinky is greater on the ball, it accelerates faster. And I used the time and the ball's position in the y-axis and the Slinky's position in the y-axis in my Python code and my CSV file. So here is my Python code. This is my visualization. I set up the background, the ball, this picture, which is basically the hand, the spring, and these are the graphs I'll show you later. The ball's mass was 0.402 kilograms. The spring's mass was 0.1 kilogram. The position of the ball at starting time was -0.6, while the velocity of the spring and the ball was at rest. Then I figured out the constant k, which is 6.78, and the relaxed length of the spring, which is 0.125. Also, I knew my time step had to be very small because it had to be an integer multiple of the time interval between the frames, and my gravity is working on both the ball and the spring, so here's the formula for those. L is used to find the length of the spring, L hat is the direction of the spring, and S is the stretch of the spring as time goes by and it's being updated. This is my spring force, and here I calculated the net force. Here is my velocity and my positions being updated for both the ball and the spring, and I used Newton's second law for that. Now let me run the code. As you can see, this is actually the ball's position as time goes by, and this is the net force acting on it. As you can see, the change in position is not very great, and that also shows that the Slinky's end is stationary as time goes by, and my diagram also shows that because it went directly on top of the ball, making the ball go downwards with the Slinky. The bottom of the Slinky remains stationary because as the center of mass is accelerating downwards, the top and the bottom accelerate towards the center of the mass of the system, which, keep in mind, is not the center of the spring because it keeps on moving. And so the Slinky is compressed to its relaxed length. And before and after the Slinky is released, the upward spring force remains the same. So the bottom of the Slinky stays stationary. So this is the upward force of the spring, and this is the downward force of the gravity before and after the Slinky is released.